Manufacturing Matters is an MFG Radio Network production brought to you by GIE Media's Manufacturing Group as industry experts take deep dives into the latest manufacturing matters, whether it's new innovations, products, technologies, and emerging markets that help you understand better why manufacturing matters to you and also to the top companies in the medical, aerospace, defense, and electric vehicle manufacturing industries.
Hello and welcome to the latest discussion from GIE Media's Manufacturing Group, how vision, measurement, and inspection ensures maximum quality control, an overview of technology options. I'm Jake Kaufman, the managing editor for GIE's Manufacturing Group of magazines, which includes aerospace manufacturing and design, today's medical developments, defense and munitions, and our online publication, EV Design and Manufacturing. We'd like to thank today's sponsor, the LS Starrett Company, founded in 1880. They are a leading global manufacturer of a range of metrology solutions, including video measurement and inspection systems, multi-sensor vision systems, optical comparators, and force measurement and material testing systems, as well as custom metrology solutions, hundreds of precision measuring tools and gauges, and more. The Starrett Metrology Division or department employs an integrated approach to vision and optical technology driven by application and dedicated to maximizing customer accuracy and throughput. Engineers and highly trained technicians design and build solutions for demanding requirements. Now, today's presenter is Greg Maish, the engineering manager for Starrett Metrology Systems. Maish has been with Starrett for 8 years and leads the design and development of vision-focused multi-axis metrology systems in Laguna Hills, California. He has a bachelor's degree in mechanical engineering from Cal State Fullerton, and prior to that, Greg was enlisted as a Marine. Without further ado, Greg, the floor is yours.
Awesome. Thanks, Jake. And happy to be here. And thanks everybody in attendance for coming to this. We appreciate, that you took some time out of your busy schedules to, come and attend our webinar. So thanks very much. All right. So Jake already did quite a good job of the introduction, but again, I'm the engineering manager here at Starrett Kinemetric Engineering. We're located in Laguna Hills, California, and we design and manufacture the vision metrology systems for Starrett, as well as we also configure and distribute many of the optical comparators as well. So just a little bit about the scope of this presentation. This is really intended to be an introduction to the different types of machine vision available on the market. I'd like to go over sort of the options that you'll see commonly out there and how they may or may not apply to your application. And really what I'd like is that everybody coming out of this would be able to evaluate one of these systems, and determine whether or not it's appropriate for their situation. And, really just it's a learning opportunity. So let's get right into it. So here's a real quick brief history on machine vision in general. Although it may seem new to metrology, it's been around for quite a long time. It was developed initially in the 60s and the 70s, and at that point it was mostly research driven, but that's really when the important edge detection, segmentation, and pattern recognition algorithms were all developed, as well as the first CCD cameras being introduced. And in fact, MIT at that point demonstrated a system that could recognize objects and patterns. However, at that point it was basically research driven and had not been implemented into the industry. But that all changed in the 1980s due to the affordability of microprocessors. It really allowed machine vision to transition from research to industrial applications. And then in the 90s, as we all know, that's when, PCs really became available widely, and it wasn't just a business machine at that point. So as Moore's law maintained, relevance and computing power increased, it really allowed, not only for them to be faster, but more accurate, more reliable, and it led to very widespread adoption in a variety of industries. In the 2000s, machine vision began to incorporate AI and machine learning to handle more complex tasks. and that's really where the beginnings of facial recognition and autonomous vehicle navigation came into play. And as not only does the computing get better, but also the cameras were getting better, and due to the higher pixel densities and faster processing, it improved the performance of these systems greatly in that time. Now, from the 2010s to the present, this is where you see the introduction of deep learning, particularly convolutional neural networks, which revolutionize machine vision. Now, those are networks that can be trained using vast amounts of data, and they can recognize objects and patterns with a very, very high degree of accuracy, and in most cases will actually surpass human capabilities, especially in specific tasks, where it's like, is the banana green enough or, yellow enough to pass inspection, that kind of thing. They're very, very good at that. All right. So, and that takes me to sort of a bifurcation of the technology, which is sort of the qualitative side versus the quantitative side. This is sort of a useful way to think about the technology. So the qualitative machine vision side is more interested and focused in sort of pattern recognition, object detection, classification, and defect and anomaly detection. And you can see that sort of here on the right hand side of the screen. You can see in the case of an autonomous vehicle, it can classify the objects within its field of view into different categories. Like we've got vehicles, pedestrians. It can figure out what the roadway is versus other and a sidewalk here, as well as in a manufacturing scenario, it can classify defects, like you can see on the bottom right, where you'd have dents of certain sizes. And this is sort of the transition to the quantitative, where it's not only classifying what they are, but sort of giving you some sort of actual objective measurement of the defect. And then there's the quantitative side of machine vision, which is more involved with precision measurement. Excuse me. And that is the side that we are involved in, being a dimensional metrology manufacturer. Precision measurement is really what we do, and that's the side that I'm going to focus on in this presentation, as it's that's our specialty in my area of expertise. So the quantitative side being more focused on the dimensional analysis and reporting of geometrical features to manufacturers, is generally, is the part in spec or is it out of spec? You have a part, you have a tolerance, and you want to know, is the part good or not? And, this type of vision metrology allows you to check for that very quickly. One of the differences is that generally these types of machines are going to require calibration and validation by a third party, generally. And that's quite a bit different than sort of the more qualitative side. And you'll usually see these in offline manufacturing scenarios where you've got sort of a quality lab, whereas the qualitative side, very often you'll see those in inline scenarios where you've got a camera and a surface light, on a manufacturing line that's checking, let's say, like a pack of pills, right, with blister packs in it. It can tell you, is the pill in the right? Does it have the logo on it? Is it missing? Is it damaged in any way? Is it broken? That being sort of the more qualitative side. So, what kind of applications should you consider machine vision for? The benefits of vision metrology are high throughput speed compared to most contacts technologies. Compared to, using hand tools, or even something more like an optical comparator, it reduces the human error because it does not require a human's judgment as far as where an edge is. So generally speaking, it reduces the sort of user-to-user variability of measurement. It's great for non-contact applications where you have soft materials, thin films, textiles, or anything that needs to be very, very clean that you just don't want to be contacted. Compared to most manual metrology methods, it is highly automated and can report and give trend analysis, and it's most appropriate for parts and objects that have projectable geometry. And what I mean by that is that, when you look at it through a camera, that surface is, matches some sort of a print, or, it basically can be flattened into a 2D plane and checked against a tolerance. Some of the challenges for the technology are transparent or reflective surfaces on objects. If you have limited light conditions where, either the lighting's highly variable or the object that you're trying to measure has poor contrast for any reason, like let's say it's an extremely matte black finish on your part and you're trying to get edges to contrast on it, it can be challenging. If you have very highly complex 3D surfaces, like imagine like a full engine block, right? That's going to be very difficult to get those features sort of square to your optical axis for measurement. It's highly dependent on the application. Sometimes it actually can be very appropriate when you have complex geometry if it's projectable, like I said before. If you have complex thread forms from like we'll see it commonly for bone screw manufacturers where they have proprietary thread forms. Those actually work really well on our machines, or even turbines. Turbine blades are another one that we see frequently. Another challenge would be large scale measurement. If the object is just simply too big, it sort of doesn't make a lot of sense for vision metrology. In those cases, you're going to want something more like a laser tracker, or use something like photogrammetry to do that sort of measurement. Let's see. So next up, I want to get into sort of common system configurations and sort of break them down into different categories, so you guys have a, hopefully a little clearer way to think about the space. So first off, what you'll see are field of view only systems. So these are effectively purely optical metrology systems. And these are, most commonly seen in the inline solutions for the qualitative side. Some of the benefits of these type of systems is that they're very fast and they use pattern recognition to figure out what it is they're looking at and perform their measurements. They're very simple to use. They don't require nearly as much training as a multi-axis, motion-controlled machine do. They typically have bigger fields of view as well as larger depths of field, meaning you can, see a wider area as well as more of the object in focus. So it allows you to measure features on different planes more easily. They're typically less expensive, have a smaller footprint, and are easier to calibrate than the the motion controlled variety. Some of the drawbacks though for these types of systems is that they generally have a limited part size based on their field of view. So if you have a very large field of view, that's great. The problem then becomes is that if you're trying to measure a very small feature in that large field of view, it becomes difficult to do so just because you don't really have enough data on, like, let's say you had a part that's 5 inches across and you're trying to measure a 1 millimeter diameter hole. You're just not going to have enough data on that hole to give you a repeatable measurement. As well as, they're typically XY planar measurement only, meaning that you can, if you have, like, let's say a height, it can be difficult or impossible to quantify that measurement using one of these systems. And so that brings me to an encoded stage system, which is really two measurement devices working in concert. In this case, you've got basically what we talked about before, which is your field of view system, and that is combined with an encoded stage device in some amount of axes, be it 1, 2, or 3, or even 4 if you have a rotary. And those work together to measure your part. So, the benefits versus the field of view only systems is that they can measure much larger parts, and it allows for higher magnification lenses to be used. Because you don't need the entire part to fit in the field of view, you can have a smaller field of view with a higher magnification measuring these small features. And, it doesn't restrict the part size in the same way that the field of view only systems do. Um, generally you'll see them, they're CNC programmable, but many of them are also manually actuated, meaning that you can move them, with your hands, and those generally are a little bit less expensive. Generally, you'll see the encoded stage systems are multi-sensor capable, and very often they are 3D capable. So now you've taken that third dimension into the measurement, and you're able to get 3D geometry, as well as, like I said before, you could even have a fourth axis where you've got a 3-axis stage as well as a rotary that's indexing your part and turning it to various different positions so you can get the geometry that you need. Some of the drawbacks is that they're going to be more expensive because they're a much more complex machine. They're more complex to operate. You're going to have to, train a user to use these. They have a bigger footprint generally, and they're more sensitive to heat and vibration. And then along with that, they're also more complicated to calibrate, because rather than just calibrating a field of view, you're doing that along with calibrating and error mapping, your motion control system. So those are sort of the two major categories you'll see out there. Within that encoded stage category, there's a lot of different subcategories. So I just wanted to give you guys a sort of a breakdown of the common ones you'll see here. The most common one that you'll see is sort of this top right, which is a vertical, what we'll either call a stage stack or an XY stage plus a Z axis. It looks, more like a microscope, where you've got your XY stage, which moves your part left and right, up and down, as well as, or forward and back rather. And then your Z axis moves your lens up and down for focus. They're very easy to learn to use, because you've got glass on them. So you've got a backlight behind your part, glass, and then your lens. And because the glass is square to the optics, if your part is prismatic, it's very simple to sort of place it on the stage and get things square to the optics so that you can do measurements appropriately. They're generally capable of 3D measurement, and very commonly you'll see them multi-sensor capable as well. What I mean by that is you may have a touch probe or some sort of laser or chromatic confocal sensor on it. And generally these will be better for square or flat parts. Sort of the big brother of this type of machine would be a vertical gantry style machine that you can sort of see in the bottom left here. Those are, in effect do the same thing. They're just larger. And you don't see these as often, just generally due to the price, and most folks don't need this kind of size, at least from what we see. But if you do need them, they are available out in the market. And they are, from a design perspective, a little bit more challenging for a guy like me, because you have to get that profile light to travel with the camera. The last one that I'll talk about here is sort of a horizontal comparator style XYZ stage. You can see sort of on the bottom right. So that will take the form more of an optical comparator, where you've got, sort of a dovetail style stage, and it's a XYZ stage stack. And then you have a interchangeable lens, and then a profile light, and then generally a surface light as well. So these are they're generally more shop hardened than they're industrial. They'll have a higher weight capacity, as well as they'll have a dovetail on the stage for fixturing, and you'll see tooling like centers and V's for these. And generally speaking, we're more likely to recommend these for turn parts. You'll see that a lot in the industry. All right. So the next thing I'd like to cover is the optical component side of the technology. So you can understand the lighting, the lens types, and sort of why you'd pick one over the other. So the first thing I want to talk about, just sort of in general, is edge detection and how these machines actually measure the edges visually. So I've got two images down here, and you can see how on one of these, you can see the points are all sort of in a cloud around. They're not in a very tight circle, whereas on the right, they are in a very tight circle. And that has to do with the, the way that I've set up the edge detection here. So, the thing we always stress is the importance of good contrast. And I have an example of what that means here, where you've got you can see on the top left, you've got an ideal digital edge where you've got, the gray to white transition is effectively, all at once. And you can see the signal to the camera would be a very, very sharp signal, right? So that means from a user's perspective, an extremely repeatable edge. To the right of that, you can see what you will actually see in real life, which is that you really have more of a gradient, meaning that as you move through from the dark to the light area, there's a, gray sort of, changing darkness gradient here. And you can see that this signal is more of a ramp rather than a sharp step. So basically, the bigger the gradient, the more challenging that edge will be to make repeatable. So you always want to try to look for something that gives you the best sort of sharpest contrast, like here on the left. And what I'm trying to show on the bottom here is how scan direction. So when you're doing edge detection, it's always scanning in a direction and then moving. Once it finds that transition, it's then moving sort of perpendicular to that scan direction to look for that edge and try to, determine where that is. So you can see on the left here, I'm scanning from the light area to the dark area, and you can see the light area is sort of the speckled, not so consistent surface finish. And because of those light and dark areas, you can see these points are all splayed out. Whereas on the right, I'm scanning from the dark area to the light area, and you can see, it's basically saying, okay, it's dark, it's dark, it's dark. As soon as I see a light area, bam, that's our edge. And you can see it's a much cleaner measurement there. And in general, you will see that, surface finishes can be challenging when it comes to vision metrology. And there's a lot of things we do to mitigate that. But it is a general challenge for the technology. So that takes me to the profile lighting. So this is, generally speaking, the primary light source used for precision measurement. You can see we have this object here on the right. Here's the difference between direct illumination versus backlight illumination. And as you can see, the contrast is much, much, much better with the backlight, right? Generally speaking, you'll see that the backlight will be a collimated backlight. Not always, but the ones that are because the light paths from a collimated light are parallel, you're going to get better contrast as well as more consistent edges with different size objects. So you want to look for that, and if precision is important to you. So one effect of light when it comes to vision metrology is the shape of the object does affect the way in which it is measured. So you'll have flat parts, sort of like a PCB. Imagine you can have a square part, imagine like a gauge block, or a round part, like a gauge pin. And the light's going to interact with all of these differently. So you want to pay attention to, basically if your application tends to be one or the other of these, you'll want to make sure that whatever it is that you're looking for is appropriate for that part. And you can see, that because the backlight gives you such good contrast, generally that's what we'll recommend. However, in a part like on the bottom left here, you can see we have features that are not able to be lit with the backlight, right? You've got these, what we call blind features, that you still may need to measure, but you cannot light with the backlight. And that's where all the surface lighting comes in. So, and surface lighting is sort of a universal challenge. You can look, it's used for blind features and also for defect detection. And there's lots of different options available out in the market. One of the more common ones is what we call a coaxial or a through the lens light. You can see that sort of in the bottom center here. The way that works is you've got a light that's literally integrated into your optics that bounces off a beam splitter onto your object and then back up into the camera. that's very, very direct and very good at providing contrast between objects that are perpendicular to your optical axis versus sort of off angle to them. It'll give you very good contrast there. The second most common one that you'll probably see is ring lighting, which is sort of this bottom right example, which gives you very flat and diffuse lighting. So that is more appropriate for objects that are not necessarily square to the optical axis. And then you'll see there's, lots of other options. You can see a dark field light. That's, the way a dark field light works is sort of in the top center here, where you've got your lights at an angle that's not, pointing down at your object. They're off to an angle. So the benefit there is you can highlight edges that are either above or below what's behind them. And then you'll see lots of different angles. You've got these diffuse domes. You'll have structured light, like this fuller partial bright field light, as well as different colors in some cases. So if you have, the different wavelengths of light also interact with different materials in a way that can, either benefit or take away from your contrast. So all those things are important when you're talking about surface lighting. And generally speaking, it's always going to just be more challenging than profile lighting for all the reasons that I've already sort of covered. Any sort of ambient light in the room is going to make it challenging. The color can make it challenging. Surface finish makes it challenging, as well as the reflectivity of the part. So yeah, just something to pay attention to. So let's get into some of the common lens types here that you'll see. The first one I want to cover is the telecentric lens. This is really when they talk about telecentricity, it's a type of optics that have all of the chief rays are parallel coming into the lens. And what that effect has, you can sort of see at the top right here, is that even though an object is more distant from the lens, it doesn't appear to shrink. What we're used to is, if you see it in a camera or even the way that your eyes work, is that as objects move away from you, they appear to be smaller. When you're doing metrology, that's a problem, because if you're measuring that, it will measure smaller. And in fact, the object itself is not smaller. So, telecentricity helps reduce that effect greatly. And most of the time you'll see a telecentric lens used in a fixed lens system. So it's either that system has a lens at a certain magnification, or it's an interchangeable lens. But generally speaking, they're always fixed. They have very consistent magnifications. They have very low distortion, and they also have a larger depth of field than most other lens types, meaning, you can have an object that's sort of taller, and the top of that object and the bottom of it will all remain in focus. And this is why you see those in those field of view only systems more commonly, because they really do, you don't need to be moving up and down in focus as much to get the object in focus. It all sort of remains that way due to the nature of the optics. They also generally tend to have a larger field of view and a longer working distance than their sort of zoom lens cousins here. And so that'll bring me to the variable zoom. Now, this one's been used for a long time. That's the one sort of on the bottom right here. The variable zoom lens is, in my opinion, the most versatile lens. They generally have a smaller field of view than the telecentric lenses, and they don't have as large of a depth of field. But because they have programmable and automatic magnification changes, you can change your magnification within a single part program and maintain your accuracy. Because of this, they're hugely beneficial if you have a variety of parts that are different sizes and different feature sizes. And yeah, they're really great at measuring a variety of stuff. So if you work in a contract inspection lab where you're never sure what it is you're going to be measuring, generally speaking, this is what we would recommend. Whereas if you're measuring a million of the same part and you have a very good idea of the feature size and the the part application, something like a telecentric lens can be more appropriate. versus the telecentric lens, they also tend to have a little bit shorter working distances, and they have auxiliary sort of lenses available on the interior that are removable that can either increase or decrease your magnification and working distance. So like I said, they're just very, very, very flexible in that way. Lastly, you'll see, you can occasionally see microscope optics on vision metrology devices. Of course, they're going to be very, very high magnification, very short working distances, meaning the lens has to be very close to the object to measure it. But they're very high accuracy. These are less common, at least in our market. However, in the semiconductor industry, these are very, very common. So yeah, that's just sort of the overview of the types of lenses you'll see in the industry. Excuse me. Next I'd like to sort of talk a little bit about cameras. So when you're selecting a system, you'll see they'll often be advertised as by the number of megapixels, right? A larger sensor is going to give you more pixels, which will give you more data for a given field of view size, generally speaking. And the large field of view systems, like the telecentric lens systems, are going to require larger sensors with more pixels because in order to get enough data on the smaller features, you need that. These larger sensors require more processing power, which is going to increase cost of the camera itself, as well as the computer needed to do the measurement. Whereas the higher magnification lenses, they can use smaller sensors, because they're able to zoom variably. They just generally don't need the sensor size that you would see on some of the larger field of view systems. So, I guess my whole point of bringing this up is that more pixels doesn't always translate to more accuracy, at least not in a way that you might, not linearly. So just to give you an example, if you have, something that's appropriately sized in your field of view on a small sensor, let's say it's taken up half of your field of view size, you're going to get great repeatability on that, even if it's a 1.6 megapixel lens. Now, if you have a 5 megapixel lens and you're with a big field of view and you're looking at that same object, but it's very small in that field of view, although the camera has more pixels total, the number of pixels measuring that small object is actually less, right? So you just have to be careful about looking at that number and saying, more equals better. It's always about how many points can you get around the object that you care about, and is that appropriate? Is that feature within your field of view appropriately sized? So, and another thing I'll say is that the difference between 10 pixels and 100 pixels on an object is huge as far as repeatability goes, but the difference between like 100 pixels and 1,000 pixels, not very big at all, actually. In fact, you may see very little difference there. So just be aware that it's not always as simple as it seems when it comes to pixel count and pixel density. So the other thing you may see is monochrome versus color cameras. Monochrome cameras, black and white. Typically, those are going to be the most accurate type of camera. And the reason for that is that most lenses are designed around a single wavelength. Green generally because that is the center of the visible spectrum. So if you have a green backlight and a monochrome camera, that's going to be your most accurate way to measure anything with a vision machine. And you'll see that again with the larger field of view systems, because they need as much accuracy as they can get with the sensor in order to measure those small features. You'll also see commonly color cameras on the market, and because for some people color is very important. If they're doing defect detection, if they're doing color accuracy analysis for like plastics or PCB manufacturers, the color can be important. So it just sort of depends on your application. As well as another thing to look at is that some cameras and systems will allow for image pre-processing, which can basically, you can change your shutter speed adjustment, which will effectively change how much light is coming into the camera. It sort of affects the sensitivity of the sensors, probably the easiest way to think about that. Where that's helpful is, let's say you're in an environment that has a lot of ambient light. If you have a shorter shutter speed and then you increase your surface lighting, the ambient light effects will be reduced, right? You can also have pre-processing that digitally increases your contrast by binarizing the image, as well as you can do some color biasing. So if you have a color camera, so those are all tools that help increase your edge contrast and will allow you to get better measurement results depending on your application. All right, so let's get into part setup and environmental considerations. So vision metrology is dependent on getting your projectable geometry of your part square with your optical axis. So fixturing can be a big deal within this space, meaning, the rigidity of the part relative to your stage, relative to your sensor are all critical. They need to be square to the optical axis. And that being said, pattern recognition and flexible coordinate systems can make that process easier. So for instance, if you have like I was talking about before, a vertical machine with a glass table, if your part is already square, you don't have to do a ton of fixturing because you can kind of just put that part down and it's already inherently square to the optical axis. Same thing would be true for a flat part like a PCB. Now, if you have, something like, let's say, a prosthetic knee that is very not square, it's a much more organic object, then in those cases, you may need some additional fixturing as well as indexing to get the profiles that you care about visible to the optical axis. Another thing to consider with fixturing would be palletizing. So very frequently we'll see customers, they'll buy, even though they're measuring small parts, they'll buy a large stage because you can put many, many parts on this stage in some sort of a pallet and have them all measured. So you can measure, 100 parts without having to reload your stage, which is, hugely beneficial for efficiency and high throughput applications. And as well as using pattern recognition, right? So if you have a pallet, you don't necessarily have to have that part in the exact same position and every single one of those little buckets. With the pattern recognition, it can just go to that area, run the pattern rec, and then orient itself and do the measurement automatically. Another consideration when it comes to part setup would be part preparation. Generally they need to be very clean. Dust, oil, and grease can all interfere with the accuracy. I have an example here on a thread where you can see there's some junk on the thread here, that can cause a part to fail when it likely should be able to pass. And that'll always be true for any kind of, optical measurement system. So it's just something to think about. The last thing I'd like to talk about in this slide is the environmental factors. So, and these are hugely important when it comes to precision. So, the biggest one being temperature control. So at the bottom here, I've got an example of thermal expansion. This is a very extreme example, but a very instructive one, I hope, which shows that as here's some train tracks here, and as the day gets hotter, these train tracks literally get longer. And as they do, the extra length has to go somewhere. So you can see this big wave here in the train tracks, right? Which is dangerous in this case. In our case, it's maybe not quite so dramatic. However, if you're measuring down to single digit micron accuracy and your temperature in your measurement room is varying by, let's say, 10 degrees Celsius, right? If you have an aluminum part that's, let's say, 500 millimeters long and is varying by 10 degrees Celsius, you could be looking at something like 11 microns worth of difference in the length of that part, just due to thermal expansion alone. So, thermal control, very, very important when it comes to metrology, as well as vibration isolation. So if, and we actually had this happen once where somebody put their machine next to a stamping press, like a huge, multi-ton metal stamping machine, and they weren't getting good results. It was like, yeah, I bet you're not, because you've got this giant machine that's shaking the entire metrology device, and that's just another thing to consider when it comes to the environment, as well as ambient light. Like I spoke about before, light coming in where you're not expecting it to can interfere with your edge detection, and particularly with surface illumination. So that brings me to software considerations, and there's quite a few different softwares out there. Sort of the main consideration being, is it a 2D, a 2.5D, or a 3D software, right? And some of the softwares can do multiple of these, but the main one is if it's sort of a 2D software which projects the geometry into sort of a flat plane, versus a 3D software at the bottom right here, which basically compares it against a CAD model, like a full 3D model. There's different use cases for each, for sure. If you're doing engine blocks, you definitely want the 3D version. If you're doing PCBs, you're probably going to want a 2D version or a 2.5D version. And when I say 2.5D, what I mean is that it's generally two-dimensional, but it can still do some height measurements and some maybe like flatness, that kind of thing. Generally speaking, the 2 and 2.5D type measurement softwares are going to be much, much easier to use and much easier to learn. Whereas the 3D type measurement software is generally, more involved. Like, generally speaking, the 2 and 2.5D, within a day or two, you could have somebody trained enough to do the application that you need them to. Whereas on a full 3D system, it could be a week or more of in-depth training. And of course, that's going to, translate to cost, not just in paying for the training, but the time of the employee as well. The other thing to consider is that if you're in a high overturn type facility, you may want to have a simpler system where you don't have to have experts who are have weeks long training. They can just it's much easier in those type of situations to have a simpler system. All the different softwares are going to have some sort of tolerancing and reporting. I'm not going to get into the details of that. It's really application dependent as to what you need. The programming methods are obviously going to have an effect. Just be aware that, again, if you have a difficult to program system, you're going to need a higher skill user. The other thing to think about is security and networking. A lot of places that will sell to have high security type requirements where they can't be networked. They have to be air gapped. In those cases, how do you share data back and forth? Yeah. How do you remote into the system if you need to do some maintenance on it remotely, that kind of thing. So, just these are sort of the considerations I would think about when it comes to selecting a software. The next thing I'll get into is sort of the calibration, validation, and accuracy of the machines. In general, these vision metrology machines need to be error mapped in some way. You need to error map the optical system. You need to error map the stage if it has one. And then you're going to need to calibrate or offset these different sensors to that stage. If you were to have a touch probe on the system, you would need to offset that to your optical axis and things like that. So just be aware of, the more large and complex the machine is, the more calibration and validation is going to be required. Generally these machines are validated against known standards, which will be very commonly chrome-on glass for machine vision. They're basically a perfectly flat and extremely accurate, optical target, which allows you to error map the optics as well as error map the stage. For touch probes, it's more common to see gauge blocks used, or gauge block stacks. And then we'll also see gauge pins and thread gauges in some cases used to calibrate the machines. Another thing I'd like to touch on is accuracy statements. I have an example here. This is one of ours. You'll see oftentimes an accuracy statement like this, where you've got some number, in this case 1.9 microns, plus a length value. So it can be a little bit confusing if you're not exposed to it. But in this case, what this implies is that we call it an E2, but in our 2D XY plane, our accuracy is 1.9 microns plus a length factor. So let's say you had a 400 millimeter object. So you'd plug 400 into this L factor here, divide by 200, which leaves you with 2. So over 400 millimeters, your max permissible error would be 3.9. So the 1.9 plus the 2. So just be aware that, it's not just that first number, it's also the length factor here. And the divisor of that length factor is going to be, huge as to what your maximum permissible error of the machine is. So just something to think about there. And then last but not least, we have some commonly available optional equipment. There'll be lots of different, like I said, types of lighting available, as well as in many cases, particularly with the vertical machines, you'll see touch probes available. The reason you'd want to consider a touch probe versus just the vision is if you have features or objects that are not sort of conducive to good edge detection. Either can't get light on them, or they're just not repeatable for whatever reason, and or for height. Height measurement is really where we'll see them used a lot. You can also have lasers and or chromatic confocal sensors available, which is another non-contact type of measurement. The thing I'll say there is that those can be highly dependent on the material. So if they're calibrated for steel, they'll work great on that, but your mileage may vary if you're then moving to a black plastic or something like that. Commonly you'll see a fourth axis available, like a rotary stage, like you can see on the bottom right here. Or in the case of, let's say if you had a dark field ring light, and a lot of times those will be on a fourth axis, so you can move that light relative to your optics to get a better edge on them. In some cases, machines will have interchangeable lenses. Some cases they won't, they'll be fixed, or you'll have a variable zoom. And then there's all kinds of fixturing available out there. Common ones you'll see centers, V's, vices, polycarbonate fixture plates for the vertical machines where you've got sort of threaded holes in like a see-through acrylic with a bunch of little fixturing parts. And those are generally, you'll see them they'll have magnets on the side of them that can be loaded onto the glass plate very repeatably. So yeah, that sort of goes over the general options that you'll see out there. And I believe that actually brings us to the end of my presentation here. Yeah, that's basically all I had for anybody today. And I think at this point, we just sort of want to open it up for questions. Thanks for your time and your patience.
Awesome. Well, thank you, Greg, for that excellent presentation. So it does look like we do have some time to hit the questions before we wrap up today. So first one coming in, looks like Rick wants to know, do these systems take better measurements than optical comparators?
Thanks for the question, Rick. In general, I would say yes, they do. And when you say better, the way I would probably describe that is more repeatable. Comparators, we still sell a lot of them. We have a lot of love for those too. It's the big difference generally is the repeatability of point collection as well as the throughput speed. So with a comparator, very frequently you're going to be using a crosshair on an edge to get that point, and depending on who's looking at that edge, there's some judgment call that has to be made on, is that crosshair exactly on that edge or is it not? And whereas with edge detection, that's all done algorithmically and it's extremely repeatable. Not to mention that actually I can go back to the slide that I had here. You can see where we've got all these points around this circle. With a vision system, all of these points are going to be collected all at once. You could have literally hundreds or thousands of points that you could collect virtually instantly. Whereas with an optical comparator, you might be collecting something like, 5 to 10 points around a circle, unless you need to know the form error. And, so it's going to be way more repeatable for both of those reasons. A, less human error, and B, far more point collection. And then, C, that added point collection also lets you see stuff like how like the form error of the circle, like how circular is my actual circle here, right? And that's a lot faster. So in that sense, I would say that vision is, yeah, I guess better, quote unquote,
Okay.
than an optical comparator. But in general, they work, principally the same way. So
Gotcha.
yep.
Okay. And then Alan wants to know, is there any comparators with edge detection?
Yes, there are. In fact, we offer them. What you'll see is usually there'll be like a little fiber optic that is on the optical comparator that goes over that edge there. Um, that helps with the repeatability greatly. So, that sort of takes out the human error component. However, the speed component compared to vision is still going to be a little bit slower, but that probably quintuples your repeatability at least compared to just doing it by eye. So yeah, those are very, very commonly available.
Okay. And are there programs available to learn how to operate these systems?
Absolutely. I mean, programs like if by programs you mean classes and things like that, yes, absolutely. We offer it, either on site or virtual training for this kind of system, and we could do it hourly. Generally what we recommend is that if you're going to buy one, that you get some training the day of installation, right? Maybe a half a day to a day of training, and then sort of work with it. And at least the way I learned and the way that I think is the best way to get acquainted with these machines is to spend, maybe let's say an hour or two a day after that initial training, becoming familiar with it. And then as you come up with questions, we have an application engineer here who can answer those, and you can, basically spend an hour with him as you need to, rather than pay for a whole day of training, just spending an hour with him on specific questions on a virtual meeting and even remote it into your system with your part is generally a very, very effective way to become trained and get your programs written. So that's we've had very good luck with that
Okay.
approach.
Gotcha. And Glenn wants to know, what is the difference between a touch probe and a CCM?
I think probably by CCM you mean a CMM, which is a coordinate
Sorry,
measuring
CMM.
machine.
Yep.
Yeah, okay, just making sure.
Yeah.
So there a CMM, at the end of the day, our machine kind of is a CMM. It's basically a CMM with with an optical probe on it that can measure throughout the field of view. So, a CMM, a touch probe, I would say, is a component of a CMM, but a CMM, generally speaking, is touch probe focused almost entirely. Um, and those machines are very similar to ours in a lot of ways, but are more focused on 3D measurement and complex measurement. And generally speaking, they're going to have lower throughput than the optical or vision type systems, just due to the contact nature of the probe. However, because of the way that they work, oftentimes they're more appropriate for doing either very, very large parts like an engine block, right? Or if you have very complex 3D geometry.
Looks like Joe wants to know if I'm going to be putting a metrology operation in at my factory, where is a good place to start?
Well, I would say it's always the best place to start is with the parts that you need to measure, right? That's really going to determine what it is you need as far as equipment goes. So what is it's super application dependent. That's how we always approach customer measurement solutions is you start with the part and what it is they need to measure. And then from there, that should inform what type of system you need. It may be vision metrology, it may not be vision metrology, right? And also, based on the system that you need, what kind of metrology area you may need to build. If you can do the measurements with hand gauging, you may not need a 68-degree metrology lab to do that. Whereas if you're doing really high throughput stuff with pallets of parts, then a vision system with a large field with a large stage is going to make a lot of sense. If you're doing the same part a million times, a field of view only system with the appropriate size magnification is going to make a lot of sense. So I would say always start with the parts that it is you need to measure, and sort of let that inform the equipment buying decision. And of course, that's really where we pride ourselves as being able to help people make those decisions, whether it's our systems or somebody else in Starrett or somebody else entirely. If it's we're not going to basically try to sell you something you don't need. So if at the end of the day what we're here to do is help you get the measurement solution that you need, and generally speaking we have a huge amount of them and can get you taken care of, and just go from there.
Okay. And then personally, I would like to know, you had talked about making sure that these systems are calibrated and things like that. What kind of leads to a system being, I guess, out of calibration, I get over the course of the manufacturing process? What sort of things lead to it needing to be calibrated?
Generally it's going to be just it depends on how much wear and tear you put on the system. So if you're running 3 shifts of pallets of parts, that thing's running 24 hours a day, it's gonna wear out. It's gonna basically go out of calibration quicker. If you are in an environment that's variable, if the room that the machine is in is varying by 20 degrees Fahrenheit every day, it's going to go out of cal quicker. Likely if you're loading super heavy parts that are at the limit of what the machine can bear, that's going to probably cause it to go out of calibration quicker. In general, what we recommend is that if you want to be sure that your machine's in cal, we offer the standards that we use to validate the machine performance. You can buy one of those yourselves for a nominal fee, and you do the calibration, or the validation of the machine, say weekly or monthly, right? And so then you can be certain that your machine's in cal. Or very commonly what a lot of customers will do is they'll have what we call like a golden part that they know measures the same. It doesn't even have to be correct. It just has to always be the same, right? You could have a part. This is the part that we're going to measure. When we run the program, if the part measures the same, your machine's measuring the same, right? So oftentimes you'll start the day, measure that part, make sure it's within the tolerance that you need it to be, and then you're good. And if you're not good, then you either call us or I guess buy the artifacts to do it yourself to get it back into specification.
Gotcha. So if we do not have any more questions, I think now would be a great time to send out a thank you to Starrett and their entire metrology department. And obviously a massive thank you to Greg Maish for today's very informative presentation. I appreciate your time today, Greg.
Hey, thanks a lot, Jake. I love doing this stuff. I'm a giant nerd at heart, so I could wax poetic about metrology for the rest of the day if you let me.
Awesome. Well, I would let you, but I do believe we have to wrap things up today. So once again, I'm Jake Kaufman from GIE Media's manufacturing department. We hope you guys all have a happy holidays, and we'll see you in 2025.
All right. Thanks, Jake.
You can listen to all of our episodes of Manufacturing Matters and Lunch and Learn podcast from the MFG Radio Network on Spotify, Apple Music, and on our websites, todaysmedicaldevelopments.com, aerospacemanufacturinganddesign.com, defenseandmunitions.com, and evdesignandmanufacturing.com.